So welcome to IMSC Diamond Jubilee Colloquium of this evening. Today's speaker is Professor Sudeshna Sinha. So Sudeshna has been our colleague, former colleague, so those of us who have known her from before, of course, need no introduction, but for the newer members of the Institute, a short biography of hers is as follows. She obtained her undergraduate degree from IIT Kanpur and then went on to do her PhD from the Tata Institute of Fundamental Research in Mumbai. She has subsequently been in the faculty of the Indian Institute of Astrophysics, then IMSC, and most recently and is presently at the Indian Institute of Science, Education and Research at Mohali. Her work in the field of nonlinear science spans over 100 papers and several patents and has been highlighted in news features ranging from Nature News and Views, Scientific American to MIT's Technology Review. She serves in the editorial board of the journal Chaos, which is published by the American Institute of Physics, and the Communications in Nonlinear Science and Numerical Simulations published by Elsevier. She was nominated Associate of the International Center for Theoretical Physics in Trieste, Italy, and is the recipient of the Birla Award for Physics and the J.C. Bose National Fellowship. She has been elected a Fellow of the Indian Academy of Sciences in Bangalore, the Indian National Science Academy, Delhi, and the Third World Academy of Sciences, Trieste. So without further ado, let me invite Professor Sudeshna Sinha to deliver the colloquium.
Thanks so much. It's on, no? Oh, okay. Right. Okay, so first off, of course, I should really thank Shitabro for taking the trouble to put this together. I mean, it's wonderful being back and, seeing some of my old friends and also seeing some of the new people, well, of course, mostly in Shitabro's group, but, at least some people in the audience whom I haven't seen before. Okay. So, well, this is kind of the end of a rather long day for us, I know. So I thought I'll keep it a little bit light and not go into too much detail about what I wanted to talk about. I thought I'd choose something which more or less bookended my stay in IMSC. It sort of started with a paper which was somewhat, around 1998, a couple of years after I joined, and ended with, say, one in about 2009, which was the year I left. So in that sense, I thought I'd choose one thread which ran through my stay here, and it was a fun ride, and it's sort of continuing to be part of my research even to this day. Okay, so so as the title says, chaos and noise in the aid of logic, and I don't think noise needs much introduction. And though I know that in this audience, especially since I've seen some of you through the day, absolutely you don't need an introduction to chaos. Still, I have a few slides and I'm going to unleash it on you, okay? And this will be a very shallow and a very, very quick, few words on chaos just to set the stage. So I sort of like to start with this spin on Wigner's classic quote, and the spin sort of replace mathematics by classical mechanics. And it always struck me, especially when I'm trying to sell mechanics 101 to people in ISA. They all think they've seen it, done that before, and they're not interested. So I try to keep telling them this, that it is unreasonably effective. And it is also extremely rigorous. So it's mathematically a very, very precise toolkit. And even if they go into a NEMS lab later or do astronomy or whatever, they will have to deal with classical objects and classical dynamics. And so in some sense, chaos is the new kid in a very old block. And of course, whenever you use the word classical, it's just a polite way of saying very old. And indeed, it's a very old field. And the only thing one can say is that chaos is a newer part of this very old way of looking at nature. And the reason, of course, it was necessary to reassess the way in which we look at the world came from a whole lot of phenomena, both in theory and in experiments, which made people, go back to the book and sort of see the implications of classical mechanics with new eyes. And so what was the surprise? The surprise was that a very large range of very simple processes seemed to give enormously complex behavior. And so complex that, at a glance, if you didn't know better, you'd think it was random forces, okay? So though behind it, ticking like clockwork were simple deterministic laws. And so, before that there was this feeling that you throw lots of complexity in and something very complicated comes out. That's not so amazing, but this was amazing because you actually had something really simple which you thought, was a very stripped down version of nature, and yet what you got out of it was very complicated. And the second thing was the word, that was the delicious contradiction of chaos, the word deterministic and unpredictable, which you never thought you'd use in the same sentence, you could now actually seem to imply each other in certain systems. And this is what made people think of a new way of viewing the classical world, and the paradigm shift is what you called, more fashionably, a new science, which is chaos theory. By new, I mean maybe like 60 years old. And to steal another book title from Ian Stewart, so does God play dice? I mean, he seems to be doing it in quantum mechanics, but there is a bit of it also in classical mechanics. And the thing is this: the present determines the future. It's a deterministic system. What else can it be? However, the approximate present does not approximately determine the future. It seems like a very simple thing, but it actually takes away that little connection between determinism and predictability. So once that thing is cut, you can actually have a perfectly deterministic system where you can't actually sensibly say anything which is predictable in the long term. And I like to also put this definition in here, that this also relates to things where you have less than perfect representation of analog values or real numbers. And so anytime you don't have infinite precision, which is almost never, and or a very perfect representation of what you're measuring, you have to deal with this thing. You have to confront this phenomena. So basically what would I call a slightly imprecise definition of chaos? It's sustained, disorderly looking, aperiodic, long-term event. Now, at my age, I'm allowed a backstory. I mean, if Spider-Man can have one, I too can have one. So this was a very, very old paper, as you can see from the date. And so I was sitting in BARC, not exactly, very insecure about my future and all that, and sort of hoping to camouflage myself like furniture and hope no one notices me and asks me to do nuclear physics or something. You sort of want to fly under the radar and do whatever you want. And so at this point, the raging concept of the day was self-organized criticality. So this was really neat concept, and in the sense, of course, Peerbach maybe oversold it, but still it's a neat concept. So people had these sandpile models. So basically there is a passive sort of sandpile with a slow driving, and in response to this drive, the pile adjusts itself in ways, and there is a whole power law distribution of events which take place, and people were very excited. But then of course I like dynamics, and I didn't think, so I thought maybe instead of this passive pile of sand, what if there is some intrinsic dynamics in the system? What if it's sort of bubbling with something which is doing on its own? And essentially that threshold activated coupling, which is sort of what the way I see sandpile dynamics, is that something piles up, it gets too much, and in good old Indian fashion you spill whatever you can't handle to your neighbors, and and you're fine. And so how about doing this same dynamics but with some intrinsic chaos in the lattice? Okay, so that was the thing, and okay, we did something. The sad part was, it was reasonably, I thought it was a nice idea, and presumably people thought it wasn't so bad because it was picked up in News and Views, but it left a slightly sad note for me, because the title, as you notice, says Abstract Models in Search of Problems, kind of like Pirandello's characters in search of a story. So here it was, I mean, he said nice things, and I think there's stuff about artists, models, something, all that felt good, but the bottom line was that it doesn't seem to have, where is it going? I mean, okay, it's a probably, cute-ish idea, but is there any use to it, okay, in some sense? And so I thought maybe many years later, well, actually not maybe that many years later, I thought I'll flip the thing backwards and say, okay, you take what you had there and think of it as a control scheme. Because what had we noticed? What we had noticed, which actually is not there in standard models of SOC, is that as you changed your threshold, your chaotic lattice became, got stabilized to different types of regular behavior. So we had noticed it. And there was a region where there was, power law scaling, and we were selling that region because we wanted to make contact with self-organized critically. Everyone wanted, so we also wanted. But this, we had noticed that, actually if we had sat down and, just looked at it as at different values, we could get very controlled regular behavior. So now what, instead of using those things, so basically migrate the idea, same idea, but put it in a different kind of spin. So you take it and use that as a scheme for control. So now let me, in a very, very briefly, say what the scheme is. Though it came from there, it actually migrated all the way to control. So it's a very simple scheme. It's like literally one line in your computer program, or as Murali later did, it is a precision clipping circuit, which he could also do very, very easily, as it happened. So what is it? All it says is, here is your dynamical system, let it be, let it do its stuff. So all you're saying is that if it exceeds a certain threshold, it's like a Lakshman Rekha, you pull it back, that's all. Okay, so you grab it and you pull it back. And so essentially you do it infrequently, because obviously it's doing its own thing, but you're putting a sort of wall in phase space beyond which it cannot wander. So at that point that's all. So you're putting a limit, a sort of your dynamic range is limited, or you can think of it as clipping some portion of your thing. Seems like a pretty innocuous thing to do, and also why should it even work? Okay, but what it does is, it takes chaos and gives all these cycles of different periodicities by setting different thresholds. So what you get is literally as if you had a chaotic temporal sequence which had all kinds of patterns in it, and you grabbed different parts of it and you stabilize them. So this snipping of it is actually sort of selecting out a pattern and giving you a controlled, stable, regular version of it. And why is chaos even nice? It's nice because it has those temporal patterns. Okay, so if you just had a simple cycle, it could only maybe make a smaller cycle or a fixed point. But chaos has so many different patterns that it could actually be clipped to all kinds of periodicities. So it's a prescriptive kind of thing where you have, what you can get out of it is a lookup table. And this engineers like, because you are not calculating much, you have done all the hard work in your at home, and you give them a table which says set threshold X and you get control period Y. And the nice part is, because you can get everything, you can give them a long list of thresholds which gives you a long list of different periods. The other nice thing for a chaos person is that these are super stable cycles. Actually, you can prove that they are super stable, and the instant you cross threshold, it gets trapped in a super stable cycle. Not only is it a stable cycle, it's also actually exceedingly robust kind of object that you get. And what you get, I would say, is a flexible pattern generator, because you have this little module which is chaotic, and you're just sending them these thresholds and it's spitting out these things. So here was a whole bunch of exact analytical results. So the thing is that for a theoretician, what makes you feel a little happy is you see stuff in computations, and then maybe you manage to get exact results which sort of agree with what you've seen. And I will absolutely not show the guts of this. That itself is a couple of hours. So I'll just say what one could find, and maybe 3 slides to intuitively give the intuitive part of it. So basically one could get the period that comes out of the chaotic system by different thresholds exactly. The second actually is a harder question. It's the reverse question. That's the one which an engineer would like, is that what threshold do we need to set in order to get a certain periodicity? That's prescription, like I want this, what do I do? So that question, as it turned out, is a bit harder question, but both could be done. The second question needs some little bit heavy duty symbolic dynamics, but otherwise it's okay. And the crux of it in 3 slides I'll say, is that you have this logistic map which is, say, a nonlinear map, and this threshold is just sort of giving a cut to the map. And all you need to know is that as you iterate from this threshold, what is the kth iterate where you will exceed threshold again. So you just need to find those solutions. And if you want the reverse question, you will have to use the inverse map. Inverse map usually these are non-invertible maps, so you have to take care of both symbols, and so that's a little more work. That was it. So basically, the other thing which we take for granted in chaos is also used, and that is ergodicity. So basically, your trajectory left to itself will wander everywhere. So if I give it a Lakshman Rekha, it's bound to cross it. So you're guaranteed that at some point it will cross it, you grab it, pull it back, reset it, and there it is trapped in the superstable orbit. Okay? So the kth iterate of the map from that point onwards, once you know when it is above x star, you have got a cycle. Okay? So for instance, this is a famous logistic map, which was the one I gave before, 4x 1 minus x. Okay? So it has a quadratic non-linearity. It was the first picture which I had. As I said, I would use it later. And as you can see that it's this beheaded map, tabletop map or whatever, some such plateau or whatever. And a flat portion is what you want, because there f prime is 0, and which would mean that is what comes in the linear stability analysis. So once it's 0, it is the most stable it can ever be. It's a superstable orbit. And so by design, you actually get all these superstable orbits. And as you change your threshold, you may not get your first fixed point, but here you get the second one, period 2. Here you get period 4. So in short, you can do this entire machinery exactly by working forward from the iterates of the map and seeing what is the solution where this inequality holds. And you have to just be a bit careful. It's a bit grungy, but it's very doable. Okay? And you get a certain function, which is the period, which is defined very precisely here. And it's, of course, a piecewise continuous function of the threshold. But the good news for people who want to implement is that these windows are nice and fairly big, so you can actually sit in them in a reasonable experimental setup and get answers, which is what, of course, later on in 2003, 10 years after that, I had the good fortune of having Murali over, and he has all these circuits, and he can do stuff which I can't do, so I got him. And I know some of you have seen this today at 11 o'clock, but I thought by 5 o'clock you would have forgotten half the pictures he's shown, so I will re-show a few of them. And so anyway, this was there. But the good part is that there was exact agreement with the small scaling, from his whatever he had in volts and what I had in the numerics, but exactly that lookup table is what was mirrored in it. And what is even nicer is that you know, his setup is in his teaching lab, or was, you know, it's not, you know, it's a standard bit of equipment. But after that, people have also worked on it. And for instance, Morai's group in Japan now have this CMOS integrated circuit implementation of 126 maps, doing exactly as we did in that analytical treatment. So, I mean, there are sometimes you feel, I mean, it has no business being this good, but it sort of works. So, that is it. Yeah. So, then I thought 2 minutes, I will extend it to a few pictures, which some of you have seen today already. So, maps are one way of looking at dynamical systems in discrete time, but of course, we more commonly use ordinary differential or differential equations. And so we tried it out on differential equations. I confess that here there are no exact results. I tried pretty hard, but I don't know, I have no ideas on it. However, the numerics is pretty extensive, and as is the experiments done by Murali and other people, you know, in other parts of the world. So here is a set of ordinary differential equations, and as you put these walls in phase space, the first one is this, you know, band which looks is a chaotic one scroll attractor. It's sort of, you know, all complicated looking. You put this thing, it starts neatly becoming cycles of different periodicities. Here's 1, 2, 4. Okay, and you can do it with double scroll. You can go from this butterfly looking. These are all oscilloscope pictures, so as real as it gets. And so here is a double scroll attractor which you have controlled into all these you know, regular dynamics, including a fixed point. Okay, this is probably burning a hole in your oscilloscope, but okay, it's sitting there. We even did it for hyperchaotic systems, because what was the feeling that, okay, we can't do this exactly, but suppose there is a hyperchaotic system. So these are systems which have more than one positive Lyapunov exponent. So to strip it of the jargon, it means that it has more than one unstable directions. Okay, so now the feeling is that it has more than one. So that, say this one has a 4-dimensional object with 2 expanding directions. So you feel you might need to put thresholding on more than one variable. You know, in one you may not just cut it, right? Because, you know, there are 2 expanding directions. But then you try one. If it works, you know, you're happy. But you're also a bit, you know, you wonder what's going on. So this was the hyperchaotic attractor, and this was the controlled orbit with one variable which was thresholded. I honestly don't know why it works this well, but it does. So basically this kind of putting a wall in phase space, even along a line, seems to be a very effective way of grabbing and controlling the rest of the dynamics. Okay, so in the next maybe 10 minutes, I thought I'll just tell you. So we are trying to do something more with it at this point. You know, I mean, if you want to use chaos, I mean, you can't say it's good for screensavers. I mean, it's a fine thing, but you have to do, you know, you might want to do something a little more serious. So one of the things we thought was, can we use this pattern generator that you have to do computational tasks, but you want to get something extra out of it, and the extra part is that you want one module with the minimum tweak, so parsimoniously, to give you flexibility. So of course, if you do lots of things and lots of things happen again, it's fine and nice, but you want to do the, you know, a very small tweak to it so that it behaves in different ways. Different avatars come by very minor tweak. And so this is chaos for computation. You can think of your hardware as these threshold activated chaotic elements, and the programming part is just that here is an input-output relation which you want satisfied. Okay, that is it. And the aim, of course, is that you should have some ability to switch. And the hope is that this will give you a more dynamic architecture, okay, that you have at hand like a raw material which could switch on the fly to be what you need it to be. So what does a theoretician need to do here? He has to set up the truth tables which you need to satisfy. You have to have a sensible way of having inputs and output. So the easiest one was to say inputs are something which you just add to the state of the system. Output, we said, was 1 if it was higher than threshold, 0 if it was lower than threshold. Very simple. But now we have to get this whole truth table to work. And to do that, suppose I went back to the, say, logistic map, for instance, or any F actually. I have to basically solve this set of equations. So this is the task which is given for in the designing part. These are necessary and sufficient conditions. Okay, you have to simultaneously solve them. And of course, you have to hope that a solution exists. That is not a given. Okay, you have to get this. And what we sort of found was that robust solutions existed only when the system is sufficiently nonlinear. So nonlinearity is needed and is something which you is actually the work engine. Okay, so that's what it's doing it. Because in some sense, if you think of it, you have these different functions which it's trying to satisfy. Obviously, a straight line somewhere is not going to cut it. You have to have, you know, some richness in your functional form to begin with in order to get all those different equations to be satisfied. And so one may say that the dynamics had that richness, and of course it's deterministic, so you're not relying on probability or something. You did it, you will get the answer in the next step. So that is a prescriptive thing. It's like a box, it's like a formula to take your state forward. Okay. This thing seems so simple, but it kept developing in all kinds of ways, and then there was this company which was developing the, oh, that should be VLSI, sorry, how could I have this typo forever? Anyway, implementation of this, and they probably have many generations now, but this was one which was given to us. I think they have been bought up by ARM and Cambridge, but okay. So people are trying to develop it, but the thing is, I don't even recognize the idea sometimes. It's got a little bit far from the way I understand it. However, I've been told that at the heart of it, it is that still the same old kind of concept which we had put forward. Okay, so the last 20 minutes, I thought I would address yet another thing, because I had promised chaos and noise, and so this is the noise bit. So noise and nonlinearity. So where does this motivation come from? I don't have to motivate it much. Of course, everybody has been talking about it. So as these devices and platforms are shrinking in size, you are increasingly going to encounter fundamental noise characteristics. So these cannot be suppressed, they cannot be eliminated, you can't just wish them away. I mean, you have to confront them in some fashion. So this was the feeling. So is there some way, again in the same thread, you know, trying to get something to work for you, just like we tried to get chaos to work for us, is there some way we can actually use noise to our advantage? Is there some, you know, scheme you can think of where the noise would work for us? That's the idea. Now the cooperative behavior between noise and dynamics is actually known, and so there was hope, and often it was known that the you know, pretty counterintuitive physical phenomena came from this interaction. For instance, stochastic resonance was one of those things, where if you give an appropriate amount of noise, it could boost signal. Okay, so it facilitates detection in a noisy environment. So you put a little bit of it, and engineers knew it for a long time. But you know, in physics, of course, we put a different framework to it. But you know, it's pretty well understood. So essentially, your SNR, your signal to noise ratio, is maximized in the presence of non-zero noise. So that was the counterintuitive part. Okay, so you know, if in fact, you can have other measures of information transfer, but the usual one says SNR. So these are maximized somewhere in the middle. Okay, and a lot of people have put a spin on a lot of phenomena to say that stochastic resonance is somehow underlying it. So what did we do? So this was, so Murali is also here. We were in it together very much. So here the search is that can we have reliable or more reliable logic circuit elements in the presence of a noise floor, which somehow is exploiting this interaction between the nonlinearity and the noise to do better. Okay? So we are trying to understand the cooperative behavior. So there is a device noise flow, can't wish it away, it is what it is. It's the nonlinearity which we can tweak, and somehow can we get them to work in a way so that in some optimal band of noise, we get the most consistent logical combination of the input signals. Okay, and well, for better or worse, we called it logical stochastic resonance, and now it appears to be a standalone term. If you Google it, it pops up everywhere. You know, you sometimes wish you'd call something somewhat better, but this is what we had called it, and it's stuck. Okay. So I'll just run through the simplest one first, and then the others would be just pictures. So take a nonlinear dynamical system. X dot is some f of x plus I, which is your low amplitude input signal, sub-threshold, somebody had asked in fact, and there is some strength of noise, and say you can take a zero mean Gaussian noise with variance 1, as you wish. Now this f of x is a nonlinear function which gives rise to distinct energy wells. Okay, so that is its thing, and you drive it with two inputs. Say you are looking for a two input gate, so I1, I2. Now remember, every time you have these two independent input signals, they can add in any old way because the world gives you inputs, you don't have a choice in the matter. So they give you a 3-level aperiodic waveform. So far everyone in stochastic not everyone, a good many, were trying to look at response to signals which were periodic. So we can't do that, don't want to do that. We are looking at aperiodic signals. So for instance, here's a simple one which has these two wells. Okay, it's bistable, and say one is around -1, one is around +1. I call one lower well, one upper well. Now the output of the system is determined by its state, whatever state it's in. So if it's in the upper well, you can call it 1. If it's in the lower well, you can call it 0. So this is a schematic. Here is your box, your nonlinear system box. Input bits given by the world, I1, I2, they are a random stream, and noise which is there, which you live with, and together they conspire to give you either something which goes up or down, and that should be the logic output corresponding absolutely perfectly with inputs if you have done your job correctly. Okay, so that's what you want. So here is a picture, and in fact, even if the other pictures don't make sense, you can carry this one back. So here are 3 panels with 3 different noise. The first one is lowish noise. Forget the scale here, it's a bit strange. The middle one is moderate noise, and the last one is high noise. High noise, well, all bets are off. I mean, it's pretty useless, right? It's, you think of 2 wells, it has a lot of noise, it's just going back and forth any which way it wants. So that is pretty useless for an output. It has no reliability at all. The strange thing is, if the noise is small, it's also not reliable. Why? It's not going back and forth, but it's getting stuck. So it might get stuck in the lower well, and somehow these inputs are not enough to drag it to the right well. So too little noise is also not working for you because of its getting stuck in the wrong place. Too much noise, it goes back and forth randomly, pretty much in its own whatever way it chooses. The middle one, on the other hand, absolutely perfectly mirrors the logic output that you want. So the bottom line here is that only in an optimal window of noise, which happened to be pretty broad actually, you have this very, very perfect kind of logic output, and very consistent. And later on, of course, various proof of principle circuit experiments were also done, and Raja Mohammed is also probably here somewhere who did some of that. Now, to push this a little further, this part was nice. We thought we'll give a little asymmetrizing bias. So we put a little constant voltage, very easy to do in real life, just put in a small C, a constant bias. And what would it do? It would swing the wells ever so slightly on one side, which would bias the output in a way so that we can match different logic. That was the logic. So you want to not only get noise assistant gates, you also want to get morphing gates from it. And so here it is, the probability. So here is bias, here is noise. This nice bright spot is the sweet spot where it's probability 1 of getting it. So we run it through 1 million random inputs. We see the output, see how well it matches. When it matches with probability 1, we are happy because it says we are good to go, and we are very confident of the output. And so this bright little spot here is the nice spot which we aim for. Okay. And this side is NOR, the other one is NAND, I think. And what it means is, as you want to get a good NAND, you put your bias in one place. You want to get a good NOR, you put your bias in another place, and you can switch from one to another because C is very, very easy, right, to tweak. So the next few things are just pictures. One was a nanomechanical oscillator, which actually operates in a nonlinear regime with 2 different vibrational states. Anytime there are 2 states coexistent, we are in business. Okay, so Mohanty's group had this in Boston University, and pretty quickly we could take what he had and do a noise-assisted reprogrammable nanomechanical logic gate. So this is a single crystal silicon, and with some, this was a schematic of what he had, and pretty small, very good power consumption also in nanowatts, and quite nifty. And this is the experimental data. Again, small noise, not great. Large noise, of course, not great. And in this middle band, pretty perfect. Then we kind of, once you get it, some of it is, you try this, that, and the other, and you would be surprised at the number of interesting systems that have double wells. So if you have one in the audience, I'd love to try it on your system. So, so here is one more example. I'm just picking up 1 or 2. So this one was, I like this example partly because I really like the cover they made for EPL. These are null clines actually, and they intersect at 4 places. These are the 4 fixed points where the null clines intersect, and this was the system which where the artist made such a beautiful one. I thought it looked like, I don't know, Montreal.
Looks like essential initials.
I never thought of that. Maybe I could sell this thing for more ways than one. Yeah, not a bad idea. True. Okay, I got a new idea today. So, right. Anyway, so here, we worked on many things. Bottom line, it works for that system. But, everything has to do something extra, right? Otherwise, you're sort of just checking it for this and that. So what it did here was, we could do, because we had 4 wells. Now first we had 2 wells. We could do stuff. We have 4 wells. We should be able to do more stuff. So what we did was, we managed to get from the 4 wells by navigating, along the null clines, 2 complementary gate operations. Okay. So what we got from 2 wells was 1. So from 4 wells thing, you needed a little bit of care because you have to guide it to the right well, but it was doable and fun. And this was a analog circuit of it done with Ed Helen, and just according to them, see, I wouldn't know because I can't do it anyway. It's all hard for me. But they said this was a little harder to implement, but at the end they got it. Moderate noise, wonderful switching, and low noise was stuck here or there. Because this is a kind of analog of the work in with Kazu and Ando. So there are lots of blurbs here and there, and the only reason I show it is some of them do a much better job of jazzing up what I'm saying than I can do, and because we need to stick to the script and all more than the journalists. However, I thought both of these did a fairly rigorous job. They didn't say anything which was wrong, at least. Okay, I know that's a very weak statement, but it's true. Okay, so there is a lot of work from other groups. And I thought I put these not because I understand them. I actually sometimes don't even understand what people are doing, though they call it LSR. So some people do theory, like they have been looking at other information-based measures, trying to decrease bit rate, error rates by using other more wells, for instance, time delay, colored noise. They've done it in different systems, physical systems, including laser systems and micromechanical systems. And thin films, I really don't know how that one worked, but I saw it, so I've put it. So in the last 10 minutes, right? I thought I'll just give a couple of, directions. I mean, I said other people are doing it. We also did some more work on it. One I thought I'd put because Manoj is here and Puneet also is here, and this was something where we used coupled systems and synchronization in order to get all the different gates. So basically you can tweak this whole idea, not just with one system, but you can get other features, like for instance, maybe how much they synchronize, and that could itself be your output. Anyway, so this particular panel was also obtained by Manoj in a nice automated way in real experiments. Usually the other ones I've shown was numerical, but this one was also obtained by sweeping parameters very efficiently, and so that's one of them. The other thing was Murali talked about in the morning, so I'll just put one slide on it. This is a recent physical review applied this year, and the idea here is, so somehow it connects the first half and the second half. So you have two wells, you have noise, so you have noise assist, so you are assisting with, noise is aiding you. However, you also want to do all possible gates. Now that is a bit harder with a bistable thing, just a plain thing. So the idea was, you have a nonlinear transformation on the input signal, and your bistable system is almost like a threshold detector. So it's a mix of logical stochastic resonance and the flexibility which you get from nonlinear transformations. And again, of course, this function has to be sufficiently nonlinear, and we found that a quartic polynomial actually yielded the full spectrum of logic functions. So again, nonlinearity to the rescue, and sufficiently nonlinear is necessary in order to do the full job. Last few minutes, I just thought I'd put this because it connects to an idea which is not part of this theme, but is going around these days, and it's called tipping. So here we were saying that there is a fixed point, there's a fixed point, okay, you go from one to another. They may be noisy fixed points. But what if we had a complex attractor here and a complex attractor there? So different parts of phase space have complex attractors, and actually you're hopping between complex attractors like a logic operation. Okay, so this is a generalized logical stochastic resonance, because you are no longer dealing with simple fixed point attractors, but could be chaotic attractors sitting in very different paths, so that you can hop between them, and the way you hop should mirror your truth table. Okay, so you switch between these different attractors. And so for instance, here is one. So one attractor is sitting here, one attractor is sitting here, and as your trajectory transits from, transfers from here to here, toggles or switches, you can get the appropriate outputs. Okay, and what happens here is, if you notice that these two things actually, if you tweak tweak the parameters can come perilously close. So actually you can have these attractors very, very close in your basin. So what does that mean? It means it takes very little to switch to the other attractor. So you can get a huge output, hugely different outcomes by a minor sort of push. So what happened was the input signal, which was, you know, order of 10 to the power minus 3, very small compared to the attractor size, which is of the order of 1. So your output is order of 1. Your input is 10 to the power minus 3. Very small change. But the dynamical outcome is huge. And in fact, this part I don't know how that happened, we have to figure it out a bit, is that the input, but this is what happened in Murali's lab, so you know, we believe experiments still. So in the proof of principle experiment, the input signal was actually sometimes, you know, he kept pushing it down 100 times smaller than the experimental noise, which was, you know, about 1 volt. So it is as if this very low amplitude input is giving this very highly amplified noise because we are utilizing that tipping point. So somehow people talk about tipping points as a very, you know, is something to be avoided because it gives you this, you know, you're pushed over the edge. There's this, you know, Bugs Bunny kind of somebody comes and pushes someone and you go screaming down the cliff kind of feeling. And it's true, but the thing is that you're using that enormous outcome, difference in outcome to work for you. That's the idea, okay? So this presumably, oh, this is my last thing. So I always manage to speak fast enough to finish on time. Okay, so this is a summarizing slide. So what was the central idea? We tried to exploit chaos in the first bit, first half, and in the second half, noise and nonlinearity. And we were trying to get this. Of course, part of it is because we are theorists. We'll just like to see what happens. But we wanted to take the let's see what happens a little further and do something a little presumably you know, of use, and that is design a computing device, which is a little different from the way it is done at this point. And at the end of the day, what we are really grabbing is the power of the nonlinear transformation. Because either you're doing it, the dynamics it on its own is doing it because it's a nonlinear evolution, so it is gifting a nonlinear transformation to it. Or if you want to engineer it, of course you can do it in as was done in the physical review applied paper, by engineered thing in the inputs, but nonlinear transformation is key. And the last thing was to somehow constructively use the jitters of noise in order to do better, at least in a wide-ish optimal window of noise, and which is right now dubbed logical stochastic resonance. Okay, so I think I'm done. Yeah. Yeah, please.
Thanks for the talk. Ma'am, currently logical gates are implemented using transistors, right? And so how is this scheme different from that, and has this the possibility of introducing some new models of building like useful computers for this whole thing?
Yeah, so that's of course what the company is trying to commercialize, right? I mean, to pack it into, you know, smaller size and with lower the power, of course, to an acceptable limit. So so the way I would put it is that the only extra idea is that when you build something with a family of something. So you maybe build it with a family of NAND gates or a family of, so you have a very static kind of art because you have one sort of logic. You can cascade it and you can, you know, concatenate and get all the others. But you have to use, you know, like you would learn in your electronics to put various things together. So, but here what you're saying is something different. It's more like you're having a programmable or reprogrammable kind of thing where almost like you are giving it the message to be what logical functionality it wants to be. So you can optimize, for instance, maybe for a task, you know, what you have, Or you could even think that, as your tasks change, you might, go on to, so you're sort of molding your hardware to to the thing. So of course, as I said, the part which is the commercialization part is, I don't even understand it, though of course it works off our patents and stuff, but I don't understand it because huge amount of other elements are there. For instance, whether the foundry can make it, whether, those are not things which we have factored in, but they are the ones that those business plan people have. But clearly, it's getting sold somewhere, mostly to do some sort of, I think, security-based thing. So
ma'am, you can turn, let's say, NAND gate into NOR gate by doing simple.
Yeah, right. I mean, proof of principle, of course. I mean, all of them have done, lots of people, I mean, not just us, other people in other groups have done it. So that's of course, without any issues, You can morph across many logic functions, That is not a problem, in proof of principle thing,
And for example, in neuroscience, we have nonlinear model of the system. So can you can such gates exist there for logical function?
So that's the kind of thing, of course, I mean, other people like Shita Branal. So their thing is, of course, I don't know, maybe I'm putting words there. So there is another way of looking at computation, is that this is nature, maybe it is doing something, it is sort of effectively doing a computation. That is not what I'm doing actually. So I am saying nature is this way, I'm using what I understood of that to exploit it. So if I don't understand what it's doing, of course I can't control it. Understanding comes before control. You know what you're controlling. So I'm using the understanding then to do something prescriptive and controlled and giving the engineers do this. The other way of looking at computation is to say that literally you can say that after all, suppose I had a fluid something, it's solving its own partial differential equation. Suppose I say that. So it's like an analog version of its, of the problem, I mean, in some ways. So that is another way of looking at things, what is it effectively doing. So I'm sure it is doing things, but in my head, actually, bio-inspired is fine. But bio has so much redundancy, it does things so differently that I don't know, whether all of it goes across as easily to the. I'm sure it's doing so many things. I mean, and it has to be nonlinear. That is for sure. I'm putting my, on the line to say that. But other than So, but to use it is that's another step actually, where you have to understand everything completely, exactly.
Thank you.
So sort of continuing the same question, sticking to the understanding part first, let's say starting from the usage part itself, why do you have to switch from one gate to other gate to other gate? I mean, when your ultimate aim is to build a useful computer, I think nowadays the way it is done is you have universal gates and like NAND gate, and from that you build other gates.
That's of course the way. I mean, most of it. But there are these I mean, you have programmable gates also, right? I mean, right. So except that most of the time, if you want to have you switch the connections and you keep the functionality of the modules thing. Here you're saying you're freeing your mind of what most engineers do. You're saying you change the functionality also. See, because after all, suppose you want to do you would have to concatenate, or you have to do you have to cascade a set of things, right, to get some other function. But yes, I mean, that is how most people do it, but you can, so the idea is to go and get a more flexible, more dynamic architecture.
Okay, I get it. It gives some sort of flexibility.
Right.
Going back to the understanding part, the framework of or the paradigm of universal gates like NAND gate or NAND logic, I think is pretty much restricted to the arena of Boolean logic.
Right.
When you are trying to understand, let's say, biological system or some nonlinear phenomena in general, why do you have to restrict to Boolean logic?
Yeah.
Or for example, is there something like fuzzy logical stochastic resonance that people have already talked about, or you flashed at some point some number of gates, right? Can you also come up with, it should be possible to come up with nonlinear oscillators which model some non-standard fuzzy logical circuit, truth table, let's say.
Absolutely.
Are people doing such things already, or it's still?
There are. That is actually probably a little bit maybe easier in some sense to do, because you have the variables and it's it's out there, and some of it could even be, as I was saying, interpretation, because it has already it's naturally doing something. You can interpret it as some sort of a computation. That there has been efforts on that. I have not done it here, so I can't speak for other people's efforts on the matter. But indeed, it's absolutely possible, and there are other ways of approaching it. So this is mine. Yeah. So yeah.
Thanks.
Yeah, but to say something, even I don't believe the brain works with Boolean logic. That's for sure. This I don't think it does. But it does some sort of effective computation, which you have to figure out. What it does is a different ball game, I think. Yeah. I don't understand her. Yeah.
So for a k input Boolean function, you have 2 power k possible logic rules. So I was just curious whether you would have, you would have so many parameter ranges to capture all of these.
Yes. Actually, but that already we have gone quite far. We have. I didn't show all that. They're usually, some of them are in. So that we have already pushed up to. I think 4. Yeah. We've already done that. It's actually not so hard. It comes out pretty neatly. Yeah. Yes, that part we have checked already.
But the size.
It is harder, obviously. Right. It is harder. You have to work harder. But the same thing goes through without any issues. So it's there. Which was our paper? I forget now. One of them, because I think Murali has done it in his own lab. So that is not, in principle, not so much of an issue so far.
Okay.
Yeah. At some point, of course, you will hit the some sort of limit in complexity.
Of course, apart from that very kind of stuff, you can also do things with multi-valued logic. Even the fuzzy logic also you can do. The thing is that how we are going to map the inputs, and then we are going to fix the performance of the system, then whether we are going to get that meaningful output or not. So at the end of the day, we need to have one-to-one correspondence between the input to the intended output. That's it. But it can be done. And we have also checked
so
multi-valued logic also
no issues. That is all very simple.
It's already there. And also we have done for multi-inputs case also.
Yeah.
So that we can do other complicated Boolean functions apart from standard logic gates kind of stuff.
Yeah. So all that part, those are not an issue. Yeah.
Other questions?
You mentioned that the noise can help to improve the signal to noise ratio in some nonlinear problems. But is it, have you seen it for semi-classical systems or beyond classical regime? Because in many quantum problems, there are these
sign problems where the signal to noise ratio is exponentially suppressed. So whether these can be exploited in quantum mechanical problems.
Yeah, you mean to say a quantum version of stochastic resonance? Yeah, I don't know. I've sort of, I mean, yeah, right. There is stuff, but I don't know how, I mean, restrictive it is because they do it for something. See, the classical version is actually, the number of examples is so huge, and it's, you know, it's very easy to understand. So I don't know if it is so extensively done for quantum. I think they're probably, I've seen 1 or 2 papers, but yeah, and so it is not as clear. Yeah, so that would, of course, there would be the issue of tunneling, and then so I don't know how meaningfully to formulate it in this way. I mean, in some sense, I agree. So at one point, it's something which I gave off at some point because I mean I was a more quantum semi-classical sort of person myself, but that connection which h cross going to 0 is a hairy limit, everyone knows, so it really messes up things. So it is sometimes very difficult to take concepts across even though the system might not be so big. What I find interesting though in this classical way of looking at it is that some of the experiments, they are really small, they are in the nanoscale, and yet the effective description is, if you strip it of everything, you can actually describe what is happening with a nice small classical equation. And once you have that model which is pakka, one can go forward without issues. But in the absence of that, I don't know how to proceed. Honest answer. Yeah.
Okay, so if there are no further questions, let's thank Professor Sudeshna Sinha for a wonderful talk.
Thank you.